Welcome to the presentation of LunarRay. LunarRay stands for Solar Dominant Hybrid Power Architecture for Scalable Lunar Power Grid. This is a student system architecture study submitted for 2026 SSP competition. I am Devesh Harish Pandey, the student researcher lead, and my co-author is Siddhi Khangar, student researcher. Our faculty advisor and head of department is Dr. Atul Deshmukh. We are from Department of Electronic and Telecommunication Engineering at GH Raisoni College of Engineering, Nagpur, India. Technical gaps in current SSP architecture. Let me first explain the 5 major technical gaps in current space solar powered architecture. First, geostationary orbit eclipse. Satellite in geostationary orbit experience approximately 70 minutes of eclipse per day, and during this time solar collection stop completely. Second, lunar nights. The moon experience 354 hours of continuous darkness, that is nearly about 15 days. Solar only system cannot survive without a massive batteries. Third, housekeeping losses. A significant fraction of solar power is consumed by the satellite-owned system before it even reaches the Earth. Fourth, microwave SSP. Conventional microwave power beam has been beam divergence required kilometer-scale reactance on the Earth. Fifth, energy storage. Batteries are heavy. At GEO launch cost, battery mass is a first-order economic problem. The diagram on the right shows our system context. The satellite in GEOs transmit power to the Earth and provides periodic support to the Moon. And here is our orbital reality check. A single GEO satellite cannot maintain continuous direct light of the sun to the moon. We acknowledge this limitation. Solar dominant hybrid architecture. Now, how does LunarRay solve this problem? The core innovation is functional decoupling of two power buses. First, the solar payload bus is dedicated exclusively to external energy delivery. No power from this bus is used for spacecraft operations. Second, the auxiliary operation bus is a low-power subsystem that handles all spacecraft operational load, including altitude control, thermal management, station keeping, and etc. Third, functional decoupling. This separates elimination parasitic drain on the solar system. Fourth, thorium continuity subsystem provides power through the lunar nights and GEO eclipse. Fifth, the key insight is that the auxiliary bus handles all housekeeping. The majority of the solar energy can be exported to the user. The diagram on the right shows how solar energy flows exclusively to external delivery, while the auxiliary subsystem provides internal operations. Structural innovation, origami deployment, and mirror swarm. Let me explain how we achieve large solar collection area despite launch volume constraint. First, origami. This is a Japanese paper folding pattern. It is a rigid foldable and deploys to a single accurate motion. Second, deployment ratio is 10:1. The operational collection area is 10 times the slotted volume inside the launching sphere. Third, modular mirror swarm. A distributed swarm of a small mirror satellite redirects additional sunlight to the main arrays. Fourth, ADCS provides pointing stability to the less than 10 microradians, achieved through star trackers and reaction wheel. Wireless power transmission. For power transmission, we choose 1550 nanometer infrared laser instead of conventional microwaves. First, the wavelength is 1550 nanometer. This is the dominant wavelength of the global optical fiber telecommunication industries. Second, atmospheric window provides 80 to 85% transmission under clear sky condition. Third, beam divergence is 1.9 microradian, computed using the diffraction limit formula. Fourth, attenuation uses cryptographic beam security. The beam only activates when a verified receiver is within the footprint. This table compares microwave with our 1550 infrared laser. Key advantages are lower beam divergence, improves safety in envelope, and reduce receive footprint. And again, lunar support is periodic or relay assistant, not continuous, available for the single geostationary orbit platform. Thermal management. It is critical for any high power space platform. First, heat pipe use sodium potassium liquid cooling. So, sodium potassium alloy with high thermal conductivity and long heritage from SNEP reactors. Second, radiators are diamond composite planes. Synthesized diamond has the highest thermal conductivity for any practical solid. Third, thermal load provides megawatt class reduction capability. Fourth, sustainability ensures design life exceeding 10 years. The diagram shows the thermal architecture. Heat flows from reactor core through the sodium potassium loop to diamond radiator plane, then radiates to deep space. Methodology system analysis framework. Our methodology is structured as a 4 stages framework. First, tool included MATLAB for link budget analysis. Second, tool includes Simulink for thermal and power flow modeling. Third, The workflow goes from architecture definition to model and simulate execution to performance metrics. Fourth, metrics include efficiency, thermal stability, and pointing tolerance. The diagram on the right shows this workflow from architecture definition to performance metrics. Simulation result, power continuity. Now let me share our key simulation result. First, power continuity during GEO eclipse. Solar generation is 200 kilowatts nominal but drops to 0 during eclipse. Auxiliary subsystem provide 30 kilowatt continuous baseload. Hybrid output maintains 125 to 200 kilowatts throughout the cycle. Net exporter provides 5 to 175 kilowatts available for external delivery. The graph shows that even during the 70 minutes eclipse, the hybrid system never drops below the operational threshold. The auxiliary subsystem ensure continuity. Simulation result, link budget analysis. Next, our link budget analysis for 1550 nanometer laser. Beam divergence is 1.89 times 10 to the power minus 7 radians. Atmospheric loss is 15 to 20% under clear sky condition. GEO received power shows conceptual feasible. Now, lunar received power is reduced but still within conceptual limit for a large aperture receiver. The graph shows normalized receiver power versus transmission distance. The red line includes atmospheric and pointing losses. The green line is the minimum receiver capture threshold. At GEO distance of 35,786 kilometers, the receiver power remains above threshold. Simulation result, thermal performance. Finally, our thermal performance of sodium potassium diamond radiator system is: nominal operation at 500 kilowatts give approximately 675 kelvins. Peak operation at 800 kilowatts give approximately 759 kelvin. Material limit is 1200 kelvin for diamond composite. Thermal margin is more than 400 kelvin at peak load, which is well within safe operating bounds. The graph follows Stefan Boltzmann behavior. The red curve is radiator surface temperature. The black dashed line is the material limit. The system maintains thermal equilibrium with significant margin. System reliability and risk governance. For reliability, we conducted a structure FMEA following ECSS standard. This table summarizes failure mode and mitigation for each subsystem, including laser transmission, reactor cooling, mirror swarm, burst power, and etc. The right side shows our development roadmap with near-term simulation validation, mid-term subsystem prototyping, and ground WPT demonstration, and long-term LEO demonstration, then GEO development. Our key reliability statement is that no single point failure exists within the primary power with continuity architecture with n+1 redundancy of critical function. Strategic roadmap. Our technology readiness level is currently TRL 2 to 3, meaning the concept is formulated and validated analytically. The target after simulation is TRL 4, meaning components validate in laboratory environment. The demonstration path follows a LEO technology demonstrator before any GEO deployment. This is a standard incremental approach for space system. The timeline shows near-term simulation validation, mid-term subsystem prototyping, and a long-term GEO demonstration, then orbital development. Finally, the conclusion. Let me conclude with what lunar ray contributes to space solar power. Architecture. Solar dominant hybrid with functional decoupling of energy buses. Power continuity. 24/7 baseload power throughout eclipse season and lunar nights. Wireless. 1550 nanometer infrared with low micro radiant divergence. Structural. Origami with 10 to 1 deployment ratio and autonomous mirror swarm. Thermal. Sodium potassium liquid metal heat pipes with diamond composite reactors or radiators. Lunar ray represent a system level feasible pathway towards space-based power delivery for terrestrial application and periodic support for emerging lunar infrastructure. This study is a student system architecture exploration. It does not represent valid hardware design for flight ready technology, but it provides a structure framework for future investigation. Thank you.